Hi guys, welcome to a new lecture series on 8085 microprocessor. This is our first video about the introduction. In this video we'll be covering the basics that is required for learning this processor 8085, and we'll be going through a quick history of the evolution of processors and so on. So that in brief is the content of this lecture. This is a very important video because if you don't understand or if you don't know the basics, it will be very difficult for you to follow the following lectures. So I would suggest you, if you are following this lecture series, to start with the introductory video. So this is the introduction. So in this lecture series we'll be covering all the functionalities and all the applications of 8085 microprocessor. If time permits, we'll also be having some lab sessions of 8085 microprocessor, the practical use of 8085 using instructions and implementation of few programs as well. So in this lecture we'll start with the introductory part and the basics which are required for learning this processor. Now the first question that arises is that why do we have to learn about 8085 microprocessor? Now 8085 microprocessor was the first commercially available microprocessor the Intel had produced. So and that was the one of the basic processors. There were processors before 8085, but one of the standard processors, you could say, is 8085. And if you want to learn higher processors or higher architectures, you should actually have your basics right. Also, why do we have to learn about processors? The reason is that we are surrounded with a lot of processors in everyday life, from your remote control to your mobile phones to your ATM machines, washing machines, your ovens, your air conditioner, your television. Each and everything contains a processor, and therefore it is good if you know how they work and what are the ways in which the data is transferred, or how these processors actually function and all these things. So 8085, we'll be learning about this processor in detail throughout this course. And what do we require a processor? As simple as that. Wherever you want to run a program, that is where a processor is required. All the programs that you have written in your life is run using a processor. If you're running those codes, definitely you will require a processor for running it. Now, simple devices like your fan and maybe your cooker or all these things doesn't require a processor. If you want to make them smart, obviously you might require a processor. These devices don't require a program to run it. It just requires a switch, and therefore these devices may not require a processor. But wherever you want to run a program, let's say your remote control, whenever you press a switch on your remote control, it has to identify which switch is being pressed, and correspondingly each switch will have a particular frequency of light, infrared light, that will be emitted, and this light will be decoded, understood in the device. Let's say if you are using a remote for a TV will recognize this light, frequency of the light or the wavelength of the light, and it will correspondingly turn it into a input. And maybe you want to change the channel, or maybe you want to increase the volume. All these things will have a particular frequency of light associated with it, and the processor will identify which switch is being pressed. Correspondingly, it will output a particular frequency light, right? So these are very simple processors. Maybe if you look at a washing machine, how does a washing machine works? Basically, if you put some clothes into the washing machine, it checks. We are talking about an automatic washing machine, definitely. So it checks the weight of the clothes, and depending upon the water level is decided, and then it starts its washing process. So in the washing process, there could be programs, there could be instructions like you have to rotate the motor in one direction for a certain period of time, and then reverse the direction, then drain the water, again rinse the water, again do the rotation process. These are very simple programs basically. So these can be done using a processor or a controller, right? So that is where you require a processor. You need to decide, you need to run a few instructions. Wherever you want to run a certain set of instructions, you will definitely require a processor for doing that. So that is the requirement of a processor. Now, what is the difference between a processor, microprocessor, and a microcontroller? A microprocessor is designed to do various applications, various tasks, like your PC, your personal computer, your laptop contains a microprocessor. Your PC can run various applications, right from your MS Word, your Excel sheets, your gamings, your Asphalt, or your Chrome, or your Paint application. A lot of applications you can run using your processor. If you go into the Microsoft what is it called, Microsoft Store, you can see a lot of applications. You can download them, and each application has each functions. They are basically nothing but programs. If you want to run various different programs, you can run those programs by downloading them from your store, and then you can use a processor for different applications. Whereas microcontrollers are designed for a specific application. Your mobile phone also has a microprocessor. In your mobile phone also you can run various different applications. But a microcontroller is designed for very specific applications. All your application based devices, like your remote control, or your washing machine, or your ATM machine, or your oven, or your television, each and every device that you have will have a microcontroller. ATM machine will run only one program throughout its life. It is not going to run the program written for a washing machine, right? It only runs one program, which is written for banking applications, for money transfer, or you want to take out some cash, you want to check the balance, you want to change the pin. All these functionalities comes under your ATM machine. You have instructions. You have probably 100 instructions or 200 instructions set for it. And a microcontroller contains a microprocessor, which is designed for a specific application, and your internal RAM, internal ROM, various input output ports, and your timers and counters, all incorporated inside a single device. So your microcontroller is something that contains your processor, IO ports, internal memory, timers, and then your serial IO. So all these things together makes your microcontroller. It is designed for specific applications, so the capability of processing will be much lower compared to a microprocessor, because microprocessors are designed for various applications. You can play music, you can watch videos, you can do whatever you want in a microprocessor, whereas in a microcontroller it is limited to one application, because the same application is done 1,000 times or 1,000,000 times in a device. Let's say your washing machine will run the same program again and again, over and over again, right? Probably there might be slight differences in the time period of your washing with different modes of operation, but it is all the same program. Basically, you will be looping it a few more times in various different modes, or the temperature you'll change, and those are random data which you put into the RAM. So that is the basic difference between a microprocessor and a microcontroller. I hope it is very much clear. Microprocessor is designed for various applications. You can do a lot of applications. Microcontroller, whereas, is designed only for a single applications. A microcontroller contains a microprocessor, a small microprocessor designed for doing one application, as well as various input output ports, internal RAM, timers, and serial IO ports, serial ports. So that's the basic difference between a microprocessor and a microcontroller. Then now let's look at what is the other basics that are required. Now, 1 bit of data. What is 1 bit? 1 bit is basically the smallest unit of data. 1 bit means 1 digit. You can either put a 0 or a 1, right? We are talking only about binary data, right? Binary numbers. Which are the binary numbers? 0 and 1. These are the only two binary numbers that we have. Base 2, right? This is the base 2 binary numbers. The smallest data unit of data is 1 bit. Then you have your 4 bit of data, which is called a nibble. A combination of 4 bits is called a nibble. Let's say 1 0 1 0 1 0 0 1. This is a combination of 4 bits. 1 0 1 1 is another combination of 4 bits. All these things can be called as a 1 nibble of data. And then comes your main unit, which is 1 byte. 1 byte is the unit that we generally use. 1 byte is 8 bits of data. We always say 1 kilobyte, 1 megabyte, or sorry, 1 kilobyte. Let's say your music files or your movie files might be of 400 megabytes, or your 1 gigabyte. Your music files may be of 2 to 3 megabytes, MB. We call it 3 MB or 1 KB or 5 KBs, 500 KB or 3 KBs, your image files, all these things, right? So this is the main unit that we are going to see. 1 byte. 1 byte is 8 bits of data. 8 bit means 8 binary digits, right? Now, what is meant by 8-bit processor? Now, 8085 is a 8-bit microprocessor. We call it 8-bit microprocessor basically because it can process 8-bit data in a single go. Is that clear? 8-bit data, it can add to 8-bit numbers, it can multiply to 8-bit numbers, it can do logical operations on 8-bit numbers, it can transfer data from one memory location to another memory location in a bunch of 8 bits in one single go. Obviously, it can do higher order numbers also. Let's say you want to add to 32-bit numbers or 64-bit numbers, you will have to do it in different cycles, multiple cycles basically, right? If you want to add to 16-bit numbers, you'll have to do it in 2 cycles, the first 8 bits in one cycle and the next 8 bits in the next cycle. So you can add then 16-bit numbers, 2 16-bit numbers. If you have a 16-bit processor, let's say you have a 8086, the next version of microprocessor, which was 16-bit processor, then you can do 16-bit operations in a single go. You can do 16-bit addition, 16-bit multiplication, division, or subtraction in a single go. Nowadays we use processors with 64-bit processor, which can do 64-bit operations in a single go. It can do addition of 64-bit numbers, or multiplication of 64-bit numbers, or data transfer of 64-bit numbers in a single go. That is what the number of bit of a processor actually represent. Now let's move on to the different types of languages. We all know there are 3 different types of languages. You have your machine level language, right? This is the language understood by the MUPI microprocessor, right? Then you have your assembly level language. We'll be learning the assembly level language throughout this entire course. In this assembly level language, we'll be using small mnemonics like add, multiply, MVI stands for move immediate data, and so on. There are a lot of mnemonics we'll be learning one by one in the upcoming lectures. So these are simple mnemonics used for, or instructions that are used in assembly level language. The processor doesn't understand these instructions. We'll have to convert these instructions into your machine level language, which is basically a combination of zeros and ones. For each instruction there will be a unique combination of zeros and ones. Is that clear? A unique combination of zeros and ones for each instruction, corresponding to each instruction, which is understood by your MUP. The microprocessor will understand only these combinations of zeros and ones. So you will require something called as a assembler to convert your assembly level language to machine level language. Then comes your high level language. High level language can be converted into your machine level language using a compiler. So in high level language, the various high level languages are C, C++, then you have your Java, and then Python, and so on, right? A lot of languages are there. So this is the simplest language that we can understand, and that's why it's called the high level language. All the instructions are very similar to your English language itself. This has to be converted using a compiler to machine level language so that the processor can understand the language. Compared to high level language, if you write your programs in assembly level language, it is much more faster to assemble them to machine level language compared to high level language. And for 8085 we only use assembly level we'll only be learning about the assembly level language. And yeah, so that is what are the three different types of languages. Then let's look at what is an opcode. Opcode, we already discussed the beginning part of opcode. Opcodes is the short form for operational code. Now opcode is basically the unique combinations that we already discussed over here. For each instruction there should be a unique opcode or a combination of zeros and ones. Only then the processor can understand these instructions. The memory, inside the memory we only store instructions in terms of zeros and ones. So 8085 has 8-bit opcodes. 8-bit opcodes means there are 8 digits which can be filled up with zeros and ones, starting from 0 0 0 0 0 0 0 0 2 up to 1 1 1 1. There are how many combinations? 2 to the power 8 different combinations, isn't it? Unique combinations. So there are, you can have 256 up to maximum up to 256 different instructions if you have an 8-bit opcode, because there are 256 different unique combinations that you can make out of these 8 bits. Is that clear? So here we have various instructions like add, mul, move. Each and every instruction will have a unique set of operational code which will be stored in your memory depending upon the program that you write. So your assembler will convert this, your multiply a comma b will be converted into the machine language by using the assembler into a unique code, unique opcode, which is in this format, a combination of 8 binary digits. And each instruction definitely should have a unique opcode. Only then the processor can identify these instructions. So all these things are already inbuilt and already decided earlier, and they have very specific opcodes set for each and every instructions. We won't be learning opcodes. I mean, we'll just analyze them. We won't learn these opcodes. Nobody can learn each and every opcode, because these are just zeros and ones, and learning the opcodes corresponding to instructions is a very difficult task. So yeah, that is what is known as an opcode. Now let's look at the basic structure of a computer system. I hope the combinations are very clear. Yeah. So let's look at the basic structure of a computer system. So inside a computer system, we can broadly classify the entire computer system into three different parts. Your microprocessor, this is your MUP, your microprocessor MUP, then your memory, and your IO, input output devices. So this is the broad classification of your entire computer system. Now, what do you put inside your memory? The memory contains two things. The first one is your programs. The second one is the data. Each and everything that goes into your memory can be either classified as a program or a data. Let's look at various examples. Let's say in your laptop, let's say you put a game. What is a game? A game is basically a program. Let's say you have an Asphalt or your Need for Speed or your PUBG. All these games are a program. Now, whatever levels or whatever files that you have put, or whatever current status of your progress in the game is loaded, or it is saved as a file, which is your data. Let's say your MS Word. MS Word is what? MS Word is a Microsoft Word is a program, and the Word files that you have created or that you have inside your memory, these are your datas. And then let's say your Chrome or your music player, your movie player, your calculator, your Internet Explorer, or your image viewer, this Microsoft Whiteboard, all these things are your programs. The images and the files that I make inside them are your data. So each and everything that goes into your memory can either be classified as a program or a data. And then comes your processor. Now how are these programs or data stored? We already discussed each and everything is stored as binary numbers. Your programs, each and every program, each and every instruction has an opcode, which is in the binary form, zeros and ones, combination of zeros and ones, which are stored in the memory. Let's say the data is also stored in the form of zeros and ones. Let's say you have a Word file. The Word file has, inside the Word file you will have probably a lot of characters, a lot of letters or images, or each and everything that you write inside your Word file. Each and every character that you write inside your Word file has a very unique ASCII code, and this ASCII code is stored in the memory in the form of binary numbers, zeros and ones, and these are stored using your flip-flops, or your in modern memories, in secondary memories, magnetic circuits are used for storing this data. But inside your RAM or ROM, the memories, in this course we'll only be generally talking about the RAM and the ROM, the primary memories. We won't be talking about the secondary memories, and the primary memories are made out of flip-flops or capacitors. So each flip-flop can hold 1 bit of data, and that is how your entire memory is made up of. And then comes your, let's say you have a music file or you have a image file. What is an image file? Image file, when you click photos in your camera, your camera might be of maybe 6 megapixel, 8 megapixel, or maybe 16 megapixel. Modern cameras come with 64 megapixels, so, or sometimes even more. So these, what do you mean by a megapixel? You have 1 megapixel. 1 mega means 2 to the power 20, right? So 2 to the power 20 picture elements are there in 1 megapixel photo. 2 to the power 20 picture elements. Picture elements means each dot is a picture element in your photo. So each dot in your photo will have a very specific color, and the color is represented using these binary codes. Let's say if you have 8 bits for representing one color, you can have 256 different shades. If you have 16 bits, then you can have 2 to the power 16, which is 65,356, I guess, or 2 to the power 16 different combination of colors for each dot of your photo. Each dot means the photo will have, entire photo will have, if you have a 1 megapixel camera, the entire photo will have 2 to the power 20 different dots, and each dot can have a different shade. And these dots, these shades are stored in the memory in the form of numbers. When you project them using a program, these come out as different colors, but whenever it is stored in the memory, it is stored as zeros and ones. So that is what goes into your memory. The memory doesn't know what it is storing. It just knows that it is storing zeros and ones. The program understands these zeros and ones and output the corresponding results that we require. Now coming to the microprocessor. I think we have covered what is a memory. Now let's come to the processor. Now, what is a processor? What does a processor do? The processor does only 3 things. That is, fetching the instructions, decoding them, and executing them. Right? Now, fetching the instruction. Where does it fetch the instructions from? Definitely the instructions are stored inside your memory. Now, whatever instructions that you have stored inside your memory should be fetched into the processor one by one in a sequential manner. And once it has fetched the instructions, it will decode them. It will try to understand these instructions, right? It tries to understand these instructions and it will execute them. Now, most students confuse decoding with converting the language. These instructions has to be converted into machine language or something of that sort. No, that is not the case. These instructions are already stored in the binary form, which is the machine language. The MUPI understands the machine language, and therefore it doesn't have to convert it. It just has to understand. Let's say you have an operational code for multiplication or maybe for division, right? The MUPI has to understand that it has to perform a division operation. So it has to understand this opcode, this unique binary code, which is of 8 bits, and it has to perform the division operation on the numbers which is coming up. So that is known as the process of decoding. Fetching means getting the instructions from the memory to the program is what is fetching means. The word itself is very clear, right? Fetch, to get the things, right? Then comes the execution. Now, what is execution? Execution means executing the instructions. There are prefabricated circuits which are already present in the microprocessor for each and every instruction that you have. So these instructions has to be executed by using these circuits. So execution is the third part that the MUPI does. The MUPI does only 3 things. It fetches the instructions, decodes them, and then it executes these instructions. Finally, we come to the IO. IO stands for input and output devices. Now, Which are the various input devices? You already know which are the various input devices. You have a keyboard, you have a mouse, you have a writing pen, or maybe a joystick. All these things are your input devices. Then comes your output devices, where you get your output. Where do you see your output? You see your output on the monitor, or maybe you print some devices, your fax machines, or all those things are used as output devices. Then comes your bidirectional device. Every day we use a bidirectional device, which is your touch screen. Your mobile has a touch screen, which is a bidirectional device. You give the input, you see your output on the screen itself. Then you have your pen drives, or your all those memories can also be used as a bidirectional device. You can read data, you can write data, all these things you can do. Bidirectional device, all these IO devices are there. So these are the basic IO devices, right? Now let's move on to the next topic. How does the MUPI fetch instructions from the memory? So how does it fetch the instructions from the memory? Now, the memory could be really huge. So each set of instructions could be at various different locations. So if you want to run a very specific program, you will have to go to that very specific memory location where the program is written. So to reach that memory location where the program is written, what do you require? You will require the address. You will always require an address to run a specific program which is at a very specific location. In the memory, each and every byte of data has a unique address. Is that clear? Each and every byte, one byte of data has a unique address, right? So you need to specify this unique address corresponding to the starting byte of your instruction. So only then it can fetch the instruction from the memory. Let's say you have a lot of programs in your PC. Let's say you have your MS Word, right? MS Word could be at a very particular memory location. Your music player program will be at another particular memory location. Whenever you click your MS Word, let's say from here, from this part, right? Whenever you click this MS Word, the processor goes to the very specific memory location in the memory where MS Word program is stored, and then it fetches the instruction and it runs the instruction, and therefore the program application starts working. Similarly, for here in 8085 also, each program that you write will be at a very specific location, and for each memory location there should be a very specific unique address, right? So address is the first thing that you need for fetching an instruction. Now, where do you put the address? You put the address on the address bus. Now there are three buses in the MUPI: the address bus, the data bus, and the control bus. Now what are bus? What is a bus? Now we know what is a bus. A bus is basically a physical wire, right? It's a physical wire. On these physical wires you put either a logic 0 or a logic 1. Now logic 0 is 0 volts, logic 1 is 5 volts. For 8085 microprocessor, for different processors, it could be of different voltage levels, but for 8085 generally we use 5 volts. 5 volts represents logic 1. Now how can you calculate the number of address lines required by any processor? Now every processor will have a maximum capacity, or the maximum amount of memory that can be connected to a processor. Every processor will have, let's say a processor that was in let's take a hypothetical processor. Let's say it can connect up to a maximum of 512 bytes only 512 bytes. Now today in your mobiles you can connect up to let's say 128. Your memory can be expanded up to 128 gigabytes, or you can extend up to 256 gigabytes. All these things you might hear. This is the same thing, like that, same thing, very similar to that. Now a hypothetical, let's say a hypothetical processor can have a maximum memory of up to 512 bytes. It's very small, definitely. Let's start with simple bytes. Now if you want to connect 512 bytes, each byte should have a unique address, right? For having a unique address, you need a unique combination of zeros and ones. How many combinations, how many address lines will be required to produce 512 unique addresses? How many lines will be required? Now what is 512? 512 is 2 to the power 9. So you will require 9 address lines, 9 different bits to represent your 1 2 3 4 5 6 7 8 9 different bits for specifying unique combinations, 512 unique combinations. Is that clear? Right, starting right from 0000000 to 11111111, 9 ones. Let's say you have just one bit. If you have just one bit, how many different combinations can you make? You can make only 0 and 1, only 2 combinations. 2 to the power 1 is 2. You have 2 combinations, unique combinations, 0 and 1. If you have only one digit, if you have 2 digits, you have 2 to the power 2, which is 4, right? 2 bits, 0 0 0 1 1 0 1 1. 2 to the power 3 is 8, which means you have, if you have 3 bits, you can have 8 different combinations starting from 0 0 0 0, sorry, 3 zeros to 3 1. There are 8 different combinations. Similarly, if you have 9 bits, you have 2 to the power 9 different combinations. You can specify unique memory locations for 512 bytes. Let's say you have 1 kilobyte. 1 kilobyte. You want to connect 1 kilobyte, at the max 1 kilobytes to your processor. How many address lines will be required? You will require 2 to the power 10 is 1 kilobyte, so you will require 10 address lines. Let's say you want to connect a maximum of up to 16 kilobytes. If you require 16 kilobytes, what is kilo? Kilo is 2 to the power 10, 16 is 2 to the power 4. You will require 2 to the power 14 is 16 kilobytes. Basically, you will require 14 address lines if you want to connect a maximum of 16 kilobytes to your processor. And let's say if you want to connect 64 kilobytes to your processor, if that is the maximum capacity that you require for your processor, how many address lines do you require? You will require, what is 64 kilobytes, that is 2 to the power 16 is 64 kilobytes. You will require 16 address lines. I hope this is very much clear. Now that is the relation between the powers of 2 and the number of unique combinations that can be formed from these bits, the combinations of zeros and ones, right? If you have 16 address lines, you can make 64 kilo different combinations, and each combination corresponds to 1 byte, and therefore you can have 64 kilobytes of memory that can be attached to your microprocessor. I hope this is very much clear. If you have any doubts, you can put it in the comment section. I'll be clearing them off as time permits. Now, which are the three different buses and what is a bus? We already discussed what is a bus. A bus is basically a physical wire. Wire means a copper wire or any kind of wire. You can see on your PCB board there are lots of wires going here and there. These are your buses basically. Now on these buses you can put either a logic 0 or a logic 1. We already discussed what is a logic 0. Logic 0 is nothing but logic 0 is 0 volt, and logic 1 is 5 volts for 8085 microprocessor. Now what is a data bus? Now once you have put the address onto the address bus, the instructions has to be fetched to the microprocessor. Always the instructions are fetched using a data bus. All the data transfer, the data fetching, the instruction fetching, everything happens through your data bus. Reading, writing, each and every process happens through data bus. The address bus is used for only putting the address, to locating the memory location. Once the memory location is located, the instructions or the data comes through the data bus. Now what is the control bus? Control bus are for generating the control signals. The control signals like read signal, write signal, release the data from some registers, or all these activate some circuits. All these things are done using your control bus. The control bus is responsible for giving the control signals to the various devices as well as internally inside the processor. Now with that, we wind up the basic introduction or the basics that are required for learning this course. All these, probably you might be knowing all these basic stuffs. If you don't know, it would have been a very good help for you guys. Now we'll just quickly go through the history and the evolution of microprocessors. We all know that the transistors were invented in 1947 by William Shockley, John and Walter at the Bell Laboratories, right? The solid state transistors. And then the invention of integrated circuits that happened in 1959. Basically, integrated circuits means these are electronic circuits, set up in electronic circuits which are formed on a single silicon wafer, right? So making of circuits, set of circuits on a single silicon wafer started in 1959, and then the various eras of integration or the integrated circuits are mentioned here. You can see these various eras from 1961 to 65. It is called the small scale integration, where we integrated 10 to 100 transistors per IC. Then you have your 1966 to 1970, where we had the medium scale integration, where we had 100 to 1000 transistors per IC. And then we have the era of 1971 to 1979, which is the large scale integration period, where we had 1000 to 20,000 transistors per IC. Then you have your 1980 to 1984, which is called as the VLSI, which is very large scale integration, 20,000 transistors to 50,000 transistors per IC. And then from 1985 we have the ultra large scale integration, ULSI, where the number of transistors are much higher, which is greater than 50,000 transistors per IC. Now let's look at the evolution of the processors. Now we have already seen the integrated circuits. Now the first microprocessor which was developed by Intel was 4004. It was a 4-bit processor. We already discussed what is a 4-bit processor, or an 8-bit processor, or a 16-bit processor. It can do 4-bit operations, 4-bit addition, 4-bit subtraction, all these operations in a single go. That is what is known as a 4-bit processor. It was developed in 1971 and it had 2300 transistors in it. Then came your 8008, which is an 8-bit processor in 1972. It had around 3500 transistors in it. And then came your 8080, which was in 1974, which is also an 8-bit processor with 66,000 transistors. Then was the first commercial microprocessor which came into the picture. That is your 8085, with a which was a 8-bit processor. It was invented in 1976. It had around 6500 transistors. Then came the next microprocessor, which is 8086. 8086 was a 16-bit processor. It had new concepts incorporated in it, like pipelining, which is a very important principle or a very important process which can increase the efficiency of the processors. We'll be learning in our coming lectures in detail what is it. So it was invented in 1978 and it had around 29,000 transistors in it. Then we came your 8088, 80186, 80286. Then came your 80386. 80386 was a 32-bit processor. The next jump was from 16-bit processor to a 32-bit processor happened in 80386 in 1985. It had around 275,000 transistors. Then came your 80486, 80586, which is also called your Pentium processor in 1993. This was the era of starting of personal computers and stuffs. This processor had 3.1 million transistors in it. And then came your Pentium 2, Pentium 3, Pentium 4. Pentium 4 came in 2000. It had around 42 million transistors. And then the Core 2 Duo processor, i3, i5, i7, i9 processors. Now here we have only discussed about the Intel processors. There were also a lot of other players like the AMD or the Motorola, and all these have also developed a lot of various processors. We didn't discuss about all those processors. We just looked at only the Intel processors. Apart from microprocessors, there were also microcontrollers like the 8048, 8051 and so on. The PIC microcontroller, the ARM microcontroller, a lot of microcontrollers in the market at Mega. We won't be looking into all these microcontrollers, but I'm just mentioning them. They are all there in the market. They were also developed during this period of time. And there are also various special purpose processors, like for digital signal processing. You have processors like a Raspberry Pi, or there are other processors also for your supercomputing workstations. Also have their processors which are different from these. They were also developed during the same period of time. So with that, we wind up our first lecture. Thank you for listening to the lecture. Have a good day.